Welcome to Module 9, Phase Diagrams, Part 1. In this glass of water, we see that we have ice and water. Both the ice and the water have identical composition, but we can see that they occur in different forms which have vastly different mechanical properties. We say that there are two phases present in this system. So what is a phase? Phase can be defined as any portion, including the whole of a system, which is physically homogeneous within itself and bounded by a surface, so that it is mechanically separable from any other portions. A phase has the following characteristics. It has the same structure, atomic arrangement throughout, roughly the same composition and properties throughout, and there's a definite interface between the phase and any surrounding objects and or joining phases. So in the example of the ice in the water, we can certainly see that within the ice it is physically homogeneous, as so in the water itself, and there is certainly a boundary, a surface between the ice and the water, and the ice is mechanically separable. We can simply put the ice water through a sieve to separate out the two components. So we can see how these definitions of a phase apply to the system we just looked at. We can express the range of temperatures, and in this case pressures, over which a phase can exist using a phase diagram. This is the phase diagram for water, or H2O, and this is a unary phase diagram because it only contains one component, which is the H2O. In such case, we have the temperature on the bottom scale and pressure on the y-axis. We can see here that at pressures, I believe this, oh no, that's not critical point. So atmospheric pressures would be somewhere between these extremes here. Let's just say it's around here. And we can see that as we increase temperature of ice, there will be a point, a certain temperature at which it then turns into water. If we keep increasing that temperature, it will then turn into steam. What we have here are what are called phase fields in the phase diagram. So the phase field for water would be this region, this area of the phase diagram. This is the phase field for ice. And this is the phase field for steam, the gas. Between the phase fields, we have a phase boundary. These characteristics of a phase diagram are common to the type of phase diagrams we'll be using for looking at, say, metal alloys. When we do go to a two-component system, we will find that there is a limit of solubility of one component in the other. We know that if we try to make a solution of sugar, if we add too much sugar, we will end up with two components. We will no longer have a single solution, so to speak, which is a single phase. So on the left here, we have a solution, which is single phase. And on the right, we have a concentrated mixture of sugar. And at the bottom of that, we have grains of sugar. So we have two phases here. And so the reason we have two phases here is because there's a limit of solubility of one component and the other. And this is something that's seen also with metals. This can be expressed on a diagram, on a phase diagram that plots composition. Here we've got, because we have two components, we've got composition here on the x-axis, and you can see that it is in weight percent of sugar. So the amount of sugar in the system expressed in terms of the weight of sugar divided by the total mass. And on the the vertical scale, we see temperature. Okay, so this is pretty common to the systems that we're going to be looking at. And we can see there's a phase boundary between the solution and the solution plus solid sugar. And we have a phase boundary between them, which expresses the solubility limit. We can see that at 0 degrees, we can put up to 60% by weight sugar into water and it will all dissolve. If we increase the temperature of the water, we can put more sugar into it. So we can conclude that if we were to put sugar in boiling water and then let that cool down, then what's going to happen is we will enter this region, this phase field here, where the sugar will precipitate out. A very similar thing is seen with metals. So let me just adjust the focus there. Here we have a phase diagram for a metal alloy of copper and nickel. The x-axis is in weight percent nickel. The 0 is given the symbol Cu, that's 100% copper. Then we go to 20% nickel, 40%, 60, 80, and then finally 100% nickel. We have temperature on the y-axis. Here we see there are 3 phase fields. The first phase field, or one of the phase fields, is the liquid phase field. Any combination of composition of the alloy and temperature that falls within this field, we expect the material will be in the form of a liquid. Similarly, any combination of temperature and composition in the field, the area that is shaded here, will be a solid. And this is the solid phase field, and it's been given the symbol alpha. So the Greek characters are usually used to describe the different, what are called solid solutions in the system. So alpha represents a solid solution of nickel in copper. There is also a third phase field here where the solid coexists, is in equilibrium with the liquid. The phase boundaries separating the 3 regions are given the name liquidus, which is the phase boundary between the mixture of the solid and the liquid. And if we're cooling an alloy, in this case, an alloy of average composition 40%, we will see that as we cool it, at this point we will have a liquid of 40% nickel composition, same here. But when we hit the liquidus, we will start to get some solid being formed. As we cool further down, we will hit the solidus. At this point, the entire material will become solid. We have unlimited solubility between copper and nickel in this case. So how do we actually create these phase diagrams? We can create these phase diagrams by creating different mixtures or different alloys of different compositions of copper and nickel, and we can melt them and then allow them to cool and monitor the temperature. We will start to see for the pure copper, we will get a thermal arrest and it will start at a certain temperature and end at the same temperature. In the case of a pure material, you see the same thing over here. In some cases, in what are called congruent transformations, you can also get the same flat part of the thermal arrest curve, even though it's not a pure material. When we have a mixture here, we will start to see a discontinuity in the temperature time curve as we see the solid starts to form here at 1190, and then at the end the solid is completely formed and we just get the usual continuation of the cooling curve. We can try this for different compositions, and from that we can determine the temperature of the solidus and the liquidus. So here's an example here. Here's the cooling curve for a particular, this is 40% weight percent nickel. And we see that this part here is where the solidus will be. Sorry about that. This is the liquidus. Yeah, this is the liquidus. So I'm not sure what that's saying there. So this will be the liquidus, and then here this will be the solidus. Okay, and we can do that for different compositions and map out the liquidus and solidus curves. Here shown in more detail is the copper nickel system. Here we're just showing a part of the system between 20 and about 55% weight percent nickel. Here we see 1, 2, 3, 4, 5 points on the phase diagram being shown for a 35 weight percent nickel alloy. At this point here, at these temperatures, it will be completely liquid and have a homogeneous composition. When we hit the liquidus, we will start to see the formation of the alpha solid solution. Now, liquid of this composition will be in equilibrium with solid of the composition shown here. We can get the two compositions that are in equilibrium within this phase field of alpha and liquid. Okay, the two where we have two phases coexisting. If we draw a horizontal line that encompasses the nominal composition, I'll go into more detail on that, then we can see the two compositions of each phase that are in equilibrium. So we can see here we have liquid of 35% weight percent nickel in equilibrium with alpha of 46%. So if we drew a line all the way down, a vertical line, and hit this, we will see that that is 46. Point C is more typical of what we're looking at with what this is called a tie line. So you see the tie line will be, we have a certain combination of temperature and average composition. That is point C. Notice that point C lies within the alpha and liquid phase field. So we know there's going to be two phases that are in equilibrium. How do we find out which phase is in equilibrium? We draw a horizontal line. Okay, so we extend a horizontal line that is coincident with C, and we extend it. To the left, we keep extending it till we hit a phase boundary. To the right, we extend it till we hit a phase boundary. We now have our tie line. Where this tie line intersects the next adjacent phase boundary, that will be the composition of the phase, which is described by whatever is just to the left here of the phase field that is just to the left of our point here. So we know that this will be the liquid composition, and the liquid composition here we can read by dropping a vertical down to the composition axes. Similarly, the intersection of the tie line with the phase boundary, the next adjacent phase boundary on the right, this will be the composition of alpha that is in equilibrium with the liquid. And once again, if we drop a vertical down from that point, we can read off the composition of the solid from the x-axis. So in this way, we can find the composition of the phases that are in equilibrium if our combination of average composition and temperature lies within a phase field that contains two phases. If the composition of the combination of temperature and average composition lie in a single phase field or a phase field with only single phase, as it does with E, then we'll just have a single phase material. What we've seen here is what we'd expect under extremely slow cooling or equilibrium cooling. If we cool quickly, we will enter non-equilibrium conditions, and there will not be enough time for homogenization of the solid phases or of the material as a whole. So what we're going to see here is the first alpha to form will be nickel rich. Okay, so it will be the 46% nickel. Then the next alpha phase to form will contain less nickel as a weight percent. And you can see that then we get a layer of 40% nickel. And this continues until we have a microstructure that is not homogeneous, okay, but contains the alpha phase with different weight percents of nickel in this manner. Well, if we were to reheat this alloy, we will see that the last solid phase to form here was the 35%, and you see that has the the 35% here. This has a lower melting point than the 46% nickel alpha phase, which was the first one to precipitate out of the melt. And so this material here will start to basically melt at a lower temperature than if it were homogeneous. And this is called hot coring or hot tearing. And it's going to be prevented by homogenizing the material by holding it at a temperature below the solidus. Okay, so we don't want to introduce any liquid when we heat treat it. We just want to give diffusion enough. We want to improve diffusion by increasing the temperature and allow it to homogenize. So we've looked at a system here where we have unlimited solubility between the two components, and there is only one solid phase. However, it is possible for there to be limited solubility between the components. In this case, we've got aluminium and antimony. You see that alpha here is what's called a terminal solid solution because it is right up against one of the y-axis that corresponds to 100% aluminum in this case, or 100% of any one of the phases. Another terminal solid solution we see is beta. Okay, so alpha is the aluminum-rich solid solution, you could say, and beta is the antimony-rich solid solution. But both alpha and beta are terminal solid solutions because they're right up against the 100% 100 weight percent vertical axes, or where the y-axis goes through a weight percent value that represent 100% of either A or B of the components. So we've got the terminal solid solutions, but we also see there's another phase, gamma. Okay, and this gamma is the compound aluminum and antimony, and you see it exists over a very tiny range of weight percent, and the ratio, the atom ratios of the aluminum and antimony are fixed. And this is an intermetallic compound. And because the ratios are fixed, this is called a stoichiometric intermetallic compound. It's also possible to have intermetallics. In this case, we see in the molybdenum rhodium system, we have gamma here, and this is an intermetallic, but it's non-stoichiometric because it can exist over a range of compositions. Once again, we have alpha and beta here as the terminal solid solutions. A number of reactions are possible. So we'll be studying in detail the eutectic, where the liquid phase splits into two solid phases, alpha and beta. We also can have a peritectic reaction where alpha and liquid react to form a third phase here, the third solid phase called beta. We have monotectic where a liquid L1 splits into liquid L2 and a solid phase alpha. Eutectoid and peritectoid are different from the three above because they occur in a solid state. Notice that there's no liquid in these reactions. In the eutectoid, you'll notice that it looks very similar to the eutectic. The eutectic occurs with the liquid phase, but the eutectoid occurs, it's entirely solid phase reaction. So we have a solid, in this case called gamma, that wants to split into alpha and beta phases. With the peritectoid reaction, we have alpha and beta solid phases that react to form a gamma phase. So out of these, we're going to get very familiar with the eutectic and the eutectoid.